we're talking about graphs and throwing terms in connection with graph theory at you. So that will continue now, certainly for this session. And the next. So for this and the next session will be on graphs. Just a whole bunch of definitions, new terms. Well, for a lot of you, maybe not so new, but not difficult. I think you'll find these concepts. They might be a bit tedious. You've just got to memorize all these terms, especially if you are not a native English speaker. All right. So let's label the graph G, big G. We'll just call this graph, any graph, big G, for G for graph, obviously. Okay. And let's label the nodes. It's points, little circles. The nodes, vertices. Vertex is singular and vertices is the plural. But I tend to use the word node, because it's just easier. So, so you have two nodes, and you label them I and j. Now, I and j, they might just be integers. I and j might be words, like names. A bit later we'll do nodes represent cities. So labeling the nodes would be giving a city name, like New York, or whatever. Okay. So, well, let's just keep it simple. Let's just say these are just integers, natural numbers, right? Counting numbers. So this pair here, that represents an edge. So in the context of graph theory, talking about the graph G, and you see this pair, I, J. So I and J, they are the labels of two nodes. Okay, and this pair here, curly parenthesis, bracket, I comma j, that means that there is an edge, a line, a connection between node I and node j. Okay, so that pair represents an edge, okay? And the edge is connecting these two nodes, node I and node j. Right? Now, you may ask, well, is the order important? Like, is this an ordered pair, or is the order irrelevant? Well, good question. It depends on the graph. For some graphs, the direction from I to j or from j to I, irrelevant, doesn't matter. Depends on the graph, depends on the context. For example, say your nodes are cities, and your edges are highways, between two cities. And highways are usually both directions. So the direction, IJ or JI, doesn't matter, it's irrelevant. Okay? But let's say your nodes are oil storage tanks, okay? And your edges then represent pipelines, oil pipelines. Now, for a given pipeline, now there's not much point, for common sense reasons, sending oil in two directions, between cities A and B, let's say. It's sort of pointless. So, oil tends to flow in one direction. So, if you have a network of oil, oil pipes, pipeline of oil, the direction is very important. So you would then have what's called a directed graph, okay, where your edges are not just lines; they're arrows, where the direction is important. But I'm jumping ahead. We'll get onto directed graphs later. So if the direction between nodes is irrelevant, not relevant, not important, that graph is called, the type of graph is called an undirected. Is that right? An undirected graph. here, like, I think you can see that. That's an undirected graph. And if the direction between two nodes is important, then it's called a directed graph. Okay, so be conscious of the distinction between the two broad categories of graph, directed and undirected. Okay. Now, if it's some authors, there are a lot of people working in graph theory. It's quite an active branch of mathematics, pure mathematics, or rather actually more applied mathematics. So if the direction is not important, then you can rewrite this as wiggly brackets instead of just parentheses, like this. And some authors do that. Okay. Now you can write your graph G as a set of sets, a set of two sets. If you think about it, it's almost common sense. So you can write it this way. These two things here are sets, and the V here, I was talking a bit about that in the previous session. This V here, it's a set, and it's the set of what? It's a set of all the vertices, or in other words, same thing, the set of all the nodes in your graph. Okay? So this V here, V for vertex, is the set of all nodes in your graph. And you can probably guess what the E is, and why E. Well, your E, that's the second set in your set of sets. This E here is the set of the edges of your graph. Okay? E for edge, obviously. Right? Now, so you can represent your graph in this form as a set or two sets. So maybe you're wondering, well, why not a wiggly bracket as a set? Good question. Anyways, that's done in the text. Okay, now, so there's a kind of description of a graph. So it's a set of vertices or nodes, same thing, and a set of the graph's edges. Okay. Now you can describe in more detail this graph in two broad ways. One is draw a diagram, like here's a repeat of one of the graphs of the previous session, and it's we've labelled the graph in the sense we've labelled the nodes. Now a bit later we will also show you the possibility where not only the nodes get labelled, or in this case ID'd if you like, given an identifier, in this case just numbered, they are numbered. Right? We can also attach IDs, we can put labels to the edges. Right? Here we have not done that, we've only labelled the nodes, the vertices. Okay? So we can expand this in more detail. Now V is the set of vertices, remember, the set of nodes. So the nodes have numbers, so here you've got a set here. Well, that's interesting. You've got curly brackets here and not here. Okay. Yeah, that's the sort of thing pure mathematicians worry more about. They like consistency. Other fields tend to be, they're not as, detailed. They pay less attention to detail. Anyway, right. So this here is the set of nodes. Okay, 1, 2, 3, 4, 5. These 5 nodes. And then we have another set, second set. Oops. Sorry. Okay. We have a set of the edges. And remember this convention. So we have an edge between 1 and 2. So we have 1, 2 here. Right? That's an edge. Now the direction is not important. But there are no arrows here. The edges are not arrowed. Right? So the direction between two nodes on an edge is irrelevant. Not relevant. Not important. Doesn't matter. Okay. So here are the list